Hey everyone, and welcome to this week's video talking about some of the things that are going on in science that normally we'd cover in class, but this being what it is this year and everything, we'll have them at home. We'll have this kind of lesson at home and everything for you. So where to begin? Let's see here. Where do we want to start for this? Let's see. Oh, here we go. Okay. We can start with this one right here. Let's start up with the joke of the day, right? Never trust an atom. They make up everything. All right, it's an oldie but a goodie. Some people, I've even seen students put this shirt on and everything. But what we're doing, we're starting chemistry, right? This is the official start of chemistry. We're finally into the second unit of the year here. While that first intro one was kind of short, this one's going to be pretty long. This will take us through almost to the holiday season, talking about chemistry and everything. So the first chapter is just kind of like an intro to chemistry, the periodic table, and atoms. And then we'll kind of move on from there with two more chapters in our chemistry unit that we have here. So what is chemistry? It's basically the study of matter, all right? What is stuff, right? Doesn't matter what the stuff is, whether it's your water bottle or the actual water that's in the bottle. What is that stuff? What is making that up, right? So that's where we're going to be talking a lot about atoms this chapter, right? And how they fit into the periodic table, the way of organizing those different atoms that are on there. Now, two big things that I want to tell you about right here, right away. We talked about this in class and personal, but just so you make sure that you get that in, there is a quiz. This is by far the biggest quiz of the entire year, is this chapter that we're in right here. And what you need to know is 40 of the elements from the periodic table, you need to know their element symbols. So on the quiz, right, I'm going to give you the word hydrogen, and you're going to need to write in the element symbol, right? So you need to put an H in there. We'll talk about this again in class, but it does matter. Hydrogen, it's a capital H, right? So that's the symbol for it. If I give you the word helium, I'll always give you the words, right? So you don't have to worry about spelling or anything like that. Just the element symbols. The symbol is capital H, lowercase e, right? That's super important. It's capital H and lowercase e. It can't be capital H and capital E or lowercase h and capital E or any other version. It's got to be capital H, lowercase e, or it's considered to be wrong. So you want to make sure that you're studying those for the quiz that's coming up, and I can even tell you the date. All right, let's see here. If you're in the A group, it's going to be on October 19th, this quiz. If you're in the B group, it's going to be October 22nd. Right, so that's when the quiz is going to be. I'll give you a piece of paper. It looks just like this one right here, except, the words are here, but the element symbols, where they are, there's just little blank spaces right there. Right, so that's going to be the quiz coming up that we'll do in class. So you want to make sure that you get that. Like I said, you don't need to know how to spell the elements, right? You just need to know, potassium, the element symbol is K. The other thing coming up is going to be the element research. There are two parts to the element research. There is this part right here where you're going to pick an element symbol this week in class, an element symbol. You're going to be picking an element this week in class, and then you need to go through and do some research about it, and then complete a project about it, right? So this is what the element research portion is going to look like. It's not designed to be super long and intensive, but just enough that you're doing a little bit of research, and then you're going to create a project about your specific element. So there'll be more about that in class for us. All right. Oh, so here you go. Here are the project due dates, and the quiz are going to both be on October 19th for the A group and October 22nd if you're in the B group. All right. So come see me in class if you have any other questions about that. But let's get on to some of the meat and potatoes of this particular week in science that we need to talk about at the very beginning here. Right. So first we have the periodic table. The periodic table is a way of organizing the elements that we know about. The basic elements that make up everything that we know of in the entire universe. Kind of like if you have a calendar, to organize your day and your week and your month and your year. Well, same thing. There's a somewhat similar kind of set of properties in the periodic table, and that it's got a repeating set of properties that happen. Just like, you might have the same schedule every Monday. You might do the same thing, like come to school. Well, same thing on the periodic table. There's a repeating pattern in those first elements going, top to bottom, up and down on the periodic table. One other thing we want to hit up really quick here, as we're starting up with chemistry, and that is the difference between mass, right, and weight. Right. So what do we mean by mass? It's basically how much stuff is inside of something, right? How many atoms are inside of this guy making the funny face right here, or how many atoms are inside of the elephant also making kind of a funny face in the picture, right? That's what we're talking about. That's what we're talking about with mass. how much stuff or how many atoms are inside of that particular object. So mass versus weight, there's a big difference. Even though here on Earth, if something is considered to be very weighty or heavy, it's also considered to have a lot of mass, but that's not true everywhere. And that's a big thing that we need to get to for us and everything. Right now, weight is basically how much gravity is pulling on something. So if you're here on Earth and let's say you weigh 100 kilograms, well, on the moon, because the moon is so much smaller, there's not as much gravity pulling on, say, the same exact person there. So you might only weigh 16.6 kilograms in this example right here, right? Or if you're an astronaut floating around on the International Space Station, for example, you don't have any weight at all, right? But your mass is still the same. You still are just as massive as you were here on Earth. So that's still staying the same. Now, that's a scale too, right? The further away from Earth you go, the less weight you have, till eventually there's no more weight at all because you're not being pulled by Earth's gravity at all, right? So the closer you are to Earth, the more weight you have, right? The further away you are, the less weight you have, right? In fact, you can actually measure that here on Earth, right? If you're close to the ocean, you have just a little bit more weight than if you're on vacation, let's say way up high in the mountains. You weigh just a little tiny bit less because you're that much further away from the center of Earth. Whereas your mass stays the same. The number of atoms inside of your body, it stays exactly the same, whether you're really close or really far away from Earth. So what happens when you're measuring gravity? The way that we measure gravity is with a scale, obviously, right? And scales fall into one of two categories. Either there's a spring being stretched, when you stand on it, the spring's being stretched, and that's determining, either in the scale or in a little mini computer, how many pounds is usually the way we're measuring that something is, or kilograms, right? Or there's a plunger that's being pushed in, doing the same thing. The further in it gets pushed, the more weight that you have. Whereas if you're using mass, right, what mass is doing is it's comparing whatever the object is, whether it's you or this really, really old cell phone right here, to a known weight, right? It's a known set weight or set mass that has already been predetermined. Because of that, right, it doesn't change, right? No matter where you take this scale right here, if you have all the same parts of the system right here, the same phone, the same weights, the same scale, if you take it to the moon, it's going to be the same, right? The mass hasn't changed. If you take it to another planet, the mass hasn't changed on Mars, right? In fact, you can use this setup anywhere at all and get the same exact results, as long as you do need a little bit of gravity, is one kind of limitation of this particular scale. But still, even if there was no gravity, the mass theoretically is still exactly the same, right? The mass of the phone right here, how many atoms are inside of it, has not changed at all. So a couple basic things that we need to get to today, right, is talking about the atom, right? The atom, it's just the basic piece of whatever element you're talking about. So you can do any element on the entire periodic table, and you can get it smaller and smaller and smaller and smaller piece of it. Eventually, you get to a point where it's such a tiny, below microscopic little tiny piece of whatever the element is, let's say titanium in this case, that you get to what's called one atom of it, right? When you get to one atom of titanium or carbon or hydrogen or whatever else you're talking about, that's the point where you can't split it anymore and still keep the properties of whatever element that is. So at that point where you have the smallest amount possible, where it's still, part of that, particular element, it keeps its same properties. That's what we call one atom of it, right? Just don't confuse atom with like a guy named Adam. That's, the example right here. Although you could get confusing when you say Adam in the picture right here, he is made of atoms. That's getting beside the point here. Okay, so information on the periodic table, it's basically, it holds all kinds of things. The periodic table is designed to be very organized. So elements in each group going up and down, well, they all have similar properties. And elements going across, they also have similar properties. The ones over here are different than the ones over there and the ones in the middle. So we'll get into all of that this chapter a little bit later, but it holds a ton of information inside of there for it. Okay, second joke, right? What is it that the waiter said when oxygen, hydrogen, sulfur, sodium, and phosphorus walked into the restaurant? What did he say? Oh, snap. Based on their symbols right here, get it? Oxygen, hydrogen, sulfur, sodium, potassium, phosphorus, potassium, okay. Okay, the last big thing that we need to get into, right, towards the end of the video here is what is it that an atom looks like? Because we do know what atoms look like, believe it or not. So I've got one little model right here, but let's kind of get into some of the parts of this. First, there is the nucleus, right? The center of the atom, right? It's the core of the atom. it's really what makes up a lot of the atom as far as its properties and things like that, is the nucleus. So it doesn't matter which element you're talking about, they all are going to have a nucleus or a center to the atom. Around the outside of it, that's where the electrons are spinning around, right? So if you've seen this popular model right here, right, the center part right here is the nucleus, the center of the atom. And in this case, these little blue things are kind of representing the electrons that are spinning around the outside of that nucleus. So here's another example right here. You've got the nucleus in the center and the electrons going around it. Or this guy right here, again, nucleus right here, electrons zipping around it. Don't confuse it with a cell nucleus, right? Cell nucleus, that's totally different. That's what we're going to get into next year. In 8th grade, you'll get into that kind of stuff and everything. Inside the nucleus, there are two parts to the nucleus, right? There are the protons, right? These protons are positively charged, and the protons, they're probably the most important part of the entire atom, right? You could call it kind of like the beating heart of the atom. In fact, all that you really need to have an atom is just the proton. If you've got just one little proton, guess what? You've got an atom of hydrogen by that, right? And so those protons, they're very important, right? They're positively charged, kind of like the positive end of a battery. They're really what gives an atom most of its properties are based on just those little protons right there. The neutrons are also packed into the nucleus, phenomenally tightly packed together there and everything. The neutrons, though, opposed to the protons being so important, while they're not unimportant, it's not that they don't do anything, but they're not nearly as important because they have no charge, so they don't seem to do quite as much to an atom as the protons do. Right? If they're not there, it does matter. There are some differences. Again, we'll get into a little bit later in the chapter, but they don't do nearly as much as the protons do. Right? If you lose a proton, then you lose the atom. If you lose the neutron, you still have an atom. Right? You can change that around and everything. So we'll talk about that a little bit later. So here we go. We got our models and everything like that. Oh, neutrons, right? Because they're neutrally charged. They're not positive or negative. They're kind of neutral. Get it like Switzerland. Okay, let's move on then to the electrons, the speed freaks of the atomic world right here and everything like that. The electrons, and again in our model right here, they're the part of the atom that are spinning around the outside of the atom, spinning around phenomenally fast. In fact, so fast they are literally almost going the speed of light, right? And so if you tried to actually do this, where you could actually see the electrons, it's almost like they're so fast. They almost move like, not so much like they're circling the nucleus of the atom, so much as they're almost like blinking in and out of existence, right? So to try to see them is phenomenal. They're moving so fast, it's almost impossible to see them. Kind of like if you've ever seen a fan, right? The fan blade spinning, right? If the fan's going full speed, did you ever try to like look and see like, there's one blade right there? It's impossible because they're moving so fast that it appears like the fan blades are moving everywhere at once. And so the electrons are kind of like that, but supercharged, much, much, much faster than even the fastest of the fans. So what does an atom look like? It's the last thing that we want to get to here and everything. Yes, we can see atoms. In fact, here's some pictures of atoms taken way back in the 1960s. We've had microscopes, now not normal microscopes. These are, well, there are several types now, but the most common one is the field ion microscope. And these microscopes are so sensitive and so precise, they can actually take pictures of individual atoms and even parts. We're getting to the point where you can almost see parts of atoms for us and everything. Now, here's a modern picture of atoms taken, and relatively recently here and everything, right? You can see there's much more detail to them and everything. And each one of these little circles is a carbon atom, right? So we've gotten very, very good at seeing atoms. In fact, nowadays, we can manipulate atoms. Right, and so here, this is a famous one. Some scientists at IBM, they were able to take individual little tiny atoms and actually, make them into, like the shape of IBM for the little symbol of IBM. Here they were having fun with Star Trek. So they've gotten pretty good at it. In fact, if you look up on YouTube, there's a whole video that they made just doing stop motion, but it's all individual atoms. Now, the next step was, let's try to build three-dimensional objects. So this one right here is really cool because this is a picture of a three-dimensional object actually made several years ago by scientists, and they made it by placing individual atoms. So each little circle right here is, one atom, right? In fact, the splotchy part's right here because it's kind of like a time-lapse picture. That's where one of the atoms moved while they were taking the picture and everything. But the key to this is right here at the very center, right? What they were trying to make is the sharpest needle in the world. Imagine a needle that's so sharp it just has one individual atom at the tip of it and everything. So sharp that if they poked you with this needle, you wouldn't even feel it. It would literally go in between the atoms in your hand, and so it wouldn't hurt at all. It wouldn't like hurt any nerves or anything like that. So you could just jab your finger all you want, and it would never hurt it because it's that sharp. Well, they actually made this, right? And in fact, the picture is like the needle is pointed straight towards the camera. So like this is the very tip of the needle right here. And the further back you go, the more and more atoms they made it to get it really sharp. So it was just kind of a practice to see, could you actually do that and everything to make really, really sharp needles. Where we're at now is they're working on making moving machines out of atoms, right? So small. You have these tiny little machines to do different tasks and everything that are so small. There's no way you could ever even hope to see it. It's way beyond just normal microscopic and everything. So this is a growing field. Can you make little machines and everything like that could do all kinds of things, super, super tiny, submicroscopic for it and everything. Also new, right? We're able to take pictures now. Here's a picture of a hydrogen atom where you can almost kind of like make out some details where the nucleus is here and the electrons is really what they're trying to get to right here are the pictures of it. And in fact, let me show you. Oh, here you go. Let me show you this short little video right here where, again, here's a picture taken with a strobe light of an atom, but you can actually see, there's some difference in where the electrons are. So we don't have the technology quite yet to look at some of those pictures like I showed you earlier. They're like, there's the proton, and there's the neutron, and here's an electron, and there's an electron. But we're getting closer. We're getting more and more, closer to being able to see, more detail about the atom all the time. All right, I hope you've enjoyed this, and we'll see you soon. Remember, try to do science always.